If you walk past a large electrical substation, you'll hear it. That distinct, low-frequency hum. It's the sound of modern civilization, but it's also the sound of money burning. Hi everyone and welcome back. That sound you hear coming from transformers. That is magnetostriction, and it is just one audible symptom of energy conversion. Today we are going to calculate exactly how well they work. We are diving deep into transformer efficiency. These static devices are incredibly efficient, often hitting 95% to 99%. But when you're transmitting gigawatts, a loss of just 1% represents enough wasted energy to power a small city. We will break down where that energy goes, derive the math for max efficiency, and explore all-day efficiency. Let's dive in. To understand efficiency, we first have to imagine a world where physics is perfect. The ideal transformer. In an ideal transformer, there is no resistance or magnetic leakage. If you put 1,000 watts in, you get 1,000 watts out. But we live in the real world. Here, the input power must supply both the load and the internal losses. The game of efficiency is about minimizing the losses. They come in two main flavors, core and copper. Let's look at the heart of the beast, the core. These are iron losses, or constant losses. They are constant because they depend on voltage and frequency, which remain stable regardless of the load connected. The magnetic domains inside the steel are constantly flipping, aligning north, then south. This molecular friction generates heat. The energy lost here is proportional to the area of the BH loop of the material. This is hysteresis loss. The second iron loss is eddy currents. These currents don't go anywhere. They just swirl inside the metal, generating heat. This is why cores are laminated. By slicing the core into thin sheets, we break the path of these currents. Now let's talk about the variable losses, the copper losses. These occur in the primary and secondary windings. Every wire has resistance. When current flows through it, power is lost as heat according to the I²R formula. Here is the catch. If you double the load current, your copper losses don't double. They quadruple. Let's put this into a formal equation. Transformer ratings are given in kVA because we don't know the load's power factor. So the full efficiency formula at any load X becomes output over output plus iron losses plus X squared copper losses. This equation tells us that a poor power factor will drag your efficiency down because you're pushing current that isn't doing real work. If you look at this graph, you see efficiency isn't constant. It starts low, peaks, and then drops as copper losses take over. As engineers, we want to know, at what exact load does the transformer perform best? The result is beautiful in its simplicity. Maximum efficiency occurs when variable losses equal constant losses. I² REQ equals P sub I. If it's a power transformer at a plant, you design for full load. For neighborhood distribution, you aim for peak efficiency at 40% load. This brings us to all-day efficiency. Distribution transformers are energized 24 hours a day, but their load varies wildly. Because core losses happen 24/7, distribution transformers are judged by all-day efficiency, a ratio of energy, not power. To improve this, we use materials like amorphous steel for the core, which drastically reduces those constant hysteresis losses. We are moving towards solid-state transformers and high-temp superconductors, but the fundamental physics will always apply. Thanks for watching. Check out the worksheet in the description for a worked example. I'll see you in the next one.